So let's continue in concavity and curve sketching. This is still from 4.4. Almost forgot that part. So this is 4.4 continued. Let's go ahead and talk about procedures for curve sketching a function. This isn't really cut and dry order you have to do it or everything that's always asked, but it's all the different things that you may be asked and kind of how to piece it together. A little bit of, so this is a lot of what I would do, and it's kind of a hybrid or similar to what the books, all the books would have. So let's go through it. Procedures for curve sketching. So you're given some function, f of x is something. So you want to consider or find the domain. So if it's a polynomial, then it's just all reals, right? It's all real numbers. You basically just move right past that real quick. But you want to consider and find the domain of f. Okay, and that has to do, so they're linked together. That has to do with asymptotes. If you have a domain where the denominator is irreducible, then, you have a 0 in the denominator, you're going to have a vertical asymptote. While you're investigating, so one is basically you are just analyzing what's given, right? You think of what type of function it is. It could be a quadratic, could be a polynomial, could be a cubic. If it's polynomial, are the degrees even or odd? You can consider symmetry. So if you have like x to the fourth and then something x squared, then you know it's symmetric about the y-axis, right? You might get something like that. Oops, something like that. Who knows? But you consider symmetry. So all the stuff that comes with just analyzing a function. This is all kind of past stuff. So you want to use all the knowledge you have first to see what the function's doing. Is it a rational function? Is it a trig function? Is it a cubic function? Is it a radical function? Is the index even or odd? All those things you look at first and kind of make note of and think about. Okay, then you can start calculating derivatives. You're basically going to need the first derivative in this chapter section no matter what. So normally you're going to calculate the first and second derivative. Okay, you may not need the second derivative. That's again, generally you will, but not all the time. Sometimes it get really complicated, and it makes more sense to use the first derivative test instead of the second derivative test. It may not ask for inflection points. Okay, but let's just go down the list and kind of the process procedure of what you would do. So you find and investigate domain, ask yourself what type of function is it, consider symmetry, and then I should say kind of etc. You keep going on just things you know. So this is known facts, maybe I should say. All right, so then calculate the first and second derivative, generally speaking. Find critical values for both the first and second derivative. Okay, and then that goes back to previous stuff, right? So where f prime is equal to 0, where f double prime is equal to 0, where f prime does not exist, and where f double prime does not exist. Those are all critical values. Okay, so we can, by doing that, we can find where f is increasing or decreasing. We can find inflection points and intervals of concavity, right? Inflection point and concavity of the graph. We can identify asymptotes, if any. Okay, and that also has to do with domain. Okay, then let's see what's next. So then we can plot values. So you have all this information. That's when you can start doing more investigation about min, max, etc. So you can plot special points, x-intercept, y-intercept, other points you may need to figure out. Okay, then by the information above, you can do your local max and min and inflection points. Okay, so you plot those. So you find them up here. We test the critical values using the first and second derivative test or second derivative test. You may need to do one or the other. Usually not. It depends on the critical value. Sometimes you just use first or the second. Depends on if it's undefined, that kind of stuff. Okay, then you may need to calculate the limit of f of x as x approaches plus or minus infinity. You're looking for basically the end behavior of the graph. So if you have a polynomial and the degree is odd, then you know it must go up on one side and down on the other, or vice versa, depending on different stuff. If it's a polynomial and the degree is even, then you know it goes up on both sides or down on both sides. So you need to consider in behavior what's going on. And so I ticked off a couple that really, this, if applicable, we won't always need to do that. So it's not a hard, fast, procedure method. You have to do these enough to kind of understand what you're doing and what you need to find, and also what's being asked. Okay, let's look at an example. And we're not going to really go down the list. That's the other thing. We're really going to answer the question. This list is just all those different things you may need to do, which we'll refer to it when needed. So given f of x is x to the fifth minus 5x cubed, find local extrema of f, discuss concavity, find inflection points, and then sketch the graph. So going back to our procedures here, process procedures, let's analyze the graph. So what type of graph is it? So that's really just this is the type. That's a polynomial, so we know it's defined everywhere. It's smooth and real. So we can make little notes of stuff. So all polynomials are continuous and differentiable everywhere. I'll just say, of course, on R. So everything's going to be defined, no D&Es. Okay, so you would not write this, but does not exist for f prime or f double prime. Okay, that's what you get with a polynomial. All right, next let's just start taking derivatives. F prime of x equal to 5 x to the fourth minus 15 x squared. Then we can start factoring that thing. Factor out a 5x squared. And we get x squared minus 3. Set that equal to 0 and solve. Okay, and I guess we'll just do it right here. So when you set that equal to 0, you're going to get 0 and what? Plus or minus root 3. So those, I'll list those down to the left there, that those are critical values. But while we're at it, let's do f double prime. And this will take an entire page. In fact, it takes actually more than a page. We'll see how it does this time. F double prime, you get 20 x cubed minus 30x. Let's go ahead and start factoring that. Factor out a 10x, left with 2x squared minus 3. Set that equal to 0 and solve. All right, so you get another critical value at 0. Don't know what's going on at 0. And then you're going to get plus or minus root 3 over 2. So when you solve this, bring over the 3, divide by 2, and then you do plus or minus the square root. Okay, so those will be your critical values. So let's list them over here. F prime critical values, x equals 0, plus or minus root 3. Don't really need to be redundant here, but that's okay. The F double prime critical values, again 0, and plus or minus root 3. So we don't know what's going on at 0. It could be an inflection point, could be nothing, could be local min or max, but we don't know yet. Okay, so now let's test everything. Let's do a chart this time, keep it organized. When you get a lot of points going on, you really want to test stuff. So we're going to test critical values. Let's just do my little chart here. Excuse me. Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, this should work. You don't have to actually draw a chart or anything. It's just trying to be a bit organized because sometimes it's difficult not to be. So I'm testing critical values for F prime. So F prime's critical values, and we're going to see whether these are, we're going to apply the second derivative test. Apply the second derivative test. Okay, so that's kind of what I'm doing there. Then I'm going to substitute into F double prime of C. So those are all my C's, right? And then, so then I'm going to say F double prime of root 3 and calculate that. I'm going to say F double prime of 0 and calculate that. Then I'm going to say F double prime of negative root 3 and calculate that. All right, so then we'll just go down the list here. Oops, I didn't mean to do that. Oops, I didn't mean to do that one either. This one is, I already knew it was 0. Okay, so when you do root 3 for F double prime, you're putting in root 3 here and doing that calculation. So I'm just going to speed things up a little bit. So you do that calculation, you get 30 root 3. Okay, and then you can, this is positive. Okay, so I'll just say sine of F double prime of C. Okay, this one's positive. This is 0. So if it's 0, what happens? It's not applicable. It fails. Test fails. So test fails if that's the case. This is negative 30 root 3, which is less than 0, so it's negative. So then you have your conclusion of those values. So positive means concave up, right? So that means local minimum. That's how I want you to remember it. Don't memorize. You got to picture, if it's positive, it's concave up. That's what you think about or memorize. Test fails though, so no conclusion at 0. So this is just for F prime. This is the second derivative test. We're not doing inflection points yet. Okay, and then negative is concave down. So that's local maximum, right? It bounces up. So local max at root 3. Okay, so that's what we're calculating. And now what I want to look at are the inflection points. Okay, so we know we'll get to that in a bit here. So now we want to do inflection points. So let's see. Okay. So what were our possible inflection points again? What are our intervals? So let's go back to here, f double prime, and here they are. So we need to look at 0, left of root, in between. So there's a whole, there's what, 4 of them. So we got to test those intervals for concave up, concave down, and we'll figure out, is it up or down, and figure out, max and min and what's going on. Okay, so you can organize this in different. I didn't do intervals here. I was just testing here on this those specific values for f prime. That's all I was doing. So now I want to do intervals for concavity. Okay, so let's write that down. We'll do. So let's just test intervals for concavity and inflection points. Okay, so that's what I want to do. That's what this one is about. All right, so let's look at the interval. And then we will pick a test value. Call it K, doesn't matter. Then we'll do f double prime at that value. And we'll do the sine of f double prime. And then the concavity. That's like your conclusion. All right. So your interval will be negative infinity up to negative root 3 over 2. And then we'll go negative root 3 over 2, and I didn't write that right. Okay, so we'll go negative root 3 over 2, 0, 0 to positive root 3 over 2, root 3 over 2, and then approach infinity. So those are our different intervals. So within that interval, choose a test value. So this is where you want to choose something easy. So to the left of negative root 3 over 2, I like to pick powers of 10. Makes it easier. Between negative root 3 over 2 and 0, pick a value. Now that you may want to do a little calculation, but if you do 3 halves, that's greater than 1. And then you do the square root is still got to be greater than 1. And so you can test negative 1. Okay, and then same rationale, you could pick 1, and then let's pick 10. So those are the test values. And you don't actually have to show that step. You really could just, kind of do it in your head and say what's going on. But you have to have some sort of organization. If you just have the graph, that's really nothing. I'm going to assume you just graphed it and you guessed. Everything has to match. So all this information must match your graph and have the rationale of what's going on. Okay, so now let's do the f double prime of k. So now you're looking at f double prime. Where is f double prime? So you don't have to show the actual value, but that's what you're calculating. Like you're going to do f double prime of negative 10, and you just need to say the sign of it. So if you go up here and you put in negative 10, well, that's going to be 20 times negative 10 to the cubed, and then plus 300 will tend to so that's way bigger. So this is going to be a huge negative number. So you just know it's negative. You don't have to show it. If it's obvious, just write it down. This is negative. Okay. If you put in negative 1, okay, I'll write it out for you. Okay, so you do the same process. I don't want to spend too much time on it. You can check yourself. So you do f double prime of negative 1, f double prime of 1, f double prime of 10, and you're looking at the sign of that. Okay, so the sign for this will be positive, this one will be negative, and this one will be positive. So this is concave down. So it's concave down, this is up. Okay, concave up, this is down, and this is up. So that's what the concavity is doing. I wrote down in my notes f double prime again here, just so we can see it better when you do those calculations. So check this. So check 20 cubed minus 30x, right? And then you have 10x, and then 2x squared minus 3. So you can actually substitute in those values and calculate if you want, or you can just kind of analyze it. Either way. So now we have just about everything except actual values to calculate. So let's see. Let's calculate intercepts. Let's do intercepts next. So we'll do x intercepts. So you set f of x equal to 0 and solve. So f of x is x to the 5th minus 5x, so it's x to the 5th minus 5x cubed equal to 0. So obviously 0 is 1. Did I just do that right? Yeah, I did. Okay, so then you factor. Let's zoom in a little bit here. Make it easier on us. Factor out x cubed. You're left with x squared minus 5 equal to 0. So of course 0 and plus or minus root 5 are our x-intercepts. All right. Okay, so those are our x-intercepts, and we already know y-intercept, right? Y-intercept, I'll just do it down here. So y-intercept is 0 f of 0. We've already established that. I guess I didn't establish it. It's just obvious, isn't it? Put in 0, you get 0. It's also one of our critical values. Okay, so what's going on there? And this will be able to tell us what's going on. This test fails, so it isn't. This doesn't tell us anything. But the concavity tells us what's going on. So it changes concavity around 0 right there. But not a local max or min. Okay, that's the key. Okay. So let's also calculate, what else do we have? Let's calculate these guys. Okay, so let's calculate root 3 and negative root 3. Let's do that. Okay, so So we have a local max at, which one was it? What was our local max? Negative root 3. And so local max will be, well, let me do min because that's it's easier to calculate. Then you can do the rest. So local minimum when x is root 3. So f of x is, I'm going to show you how to do this. X to the 5th minus 5x cubed. So if we do f of root 3, then that's 3 raised to the 5 halves minus 5 times 3 raised to the 3 halves. Excuse me. Then you can factor out a 3 to the 3 halves. And you're left with basically just 3 minus 5. This is not obvious, but check that. So then you get negative 2 times 3 to the 3 halves. So that's negative 2 root 3 cubed. So that's negative 2 times 3 root 3. So that's just negative 6 root 3, which is approximately negative 10.4. So this, and then if we do f of negative root 3, you're going to get the positive case. You're going to get 6 root 3, and that's approximately positive 10.4. So we'll know how to graph it then a bit. All right. Okay, so normally I won't give you such messy work on an exam, but that's how you can calculate a radical like that and get into one term. So just, I want you to practice it, check it out. So now we want to graph, and I'm going to have to come down here to graph. We don't have enough room. Okay, so let's do our graph. And I think I can do this almost to scale. Well, not exactly, but we're going to count off on 2s, I believe. So you want to get your points close. I told you this was going to be long. It's a whole page. Okay, so you want to do, what approximately are these values to get the points done right. So let's go to our intercepts, negative root 5 and positive root 5. Okay, so coming back up here, negative or root 5 is approximately what? It's got to be what? Between 2 and 3, right? Because 2 squared is 4 and 3 squared is 9. So it's got to be, we'll just say it's 2.236. So we'll just say 2.3. I said 2.3. It's 2.23. So 2.2. So it's almost 2.23, whatever. So we're going to graph that. 1, 2, 3. 1, 2. Yeah, I didn't really graph it to scale. So 1, 2, and then a little bit. Be right here. So that's an intercept. That is root 5. And then 1, 2, and then a little bit. So it's right here. That's your negative. That's your other intercept at negative root 5. And then it's concave down from negative infinity to root 3 over 2. Okay, and then what is your other radical? your local min and max. So oops, I hate when that does that. So this is your max. Okay, that's your min. So we want to get root 3. It's approximately what? 1.7. So this is 1, so it's just a little bit here. And we go up to 10.4. So we'll do 2, 4, 6. So we'll do 2, 4, 6, 8, 10. We'll call it this value right here. Oops, and then a little bit. So you go up to this value. Here's 10, and then a little bit. So we'll go right about here. And you just label it. Okay, so that point up there is negative root 3, and then 6 root 3. And then you have a negative case for the positive root 3. So it is positive is 1, so it's 1. I didn't quite do that right, did I? So it's, do this here. So this is 1, and that's 2, so it's 1.7. So we're going to call it right about here. And then you go up to, say, here. And it's concave down, so it's doing this. It's a local max. It's doing that kind of thing. Okay, and I'm going to erase that. Okay, and then now we do, those were negatives. Negative, negative, negative. Now we go to, here's 1, and then 1.5, 1.7 is going to be right about here. And then you go down 2, 4, 6, 8, 10.4. So it's right about there. So that is that's your other critical value. That is your local minimum, root 3, negative 6 root 3 is right there. And it's concave up from the root 3 over 2 to there. So you still want to get an approximation for root 3 over 2. It's going to be in between that, of course, but just so you can plot it. Okay, so I'm getting that calculation. It's 1.2. 2, but that's okay, close enough. Did I get a value for that? At one point, our inflection point? I don't think I did. So you still have to calculate that. So that's f of 1.2. This is just to get your rough sketch so you can have an idea of it. 1.2. So f of 1.2 should be negative because it's going to be down here. It's going to be down here. So we know it's concave down. It's going to be a max here. And then what happens at 0? So there's an inflection point somewhere in here. And then at 0, you do get a horizontal asymptote. It's horizontal. But then it does something like this and then goes back up. Okay, so this might be kind of tough to graph. So the other one's going to be negative 1.2, so it's going to be probably right here as an inflection point. So let's do that calculation just to see what it is. Excuse me, I'll do it on a calculator. I don't think I have it in my notes. I don't see it. So I have the local min and max, but not the inflection point. So root. Wait a second. Yeah, I don't have that on my notes. Okay, so we'll do a quick calculation just to get the approximation of the graph. So where's my function? Function's way back up here. So it's 5. We're going to have to grab this thing. No, not that one. Okay, it's not there. I'll put it right about here. All right, so you get 1.2 to the 5th minus 5 times 1.2 cubed. This is where this would be fine for these values. I usually don't ask you to get too, when it takes this is taking what, almost 30 minutes just to do this problem. So 1.2 to the 5th, oops, wrong button, 1.2, and this is a rough calculation because the rounding errors are going to be horrendous. And then 5 will be negative, and then 1.2 to the 3rd. You multiply that, and you add. So I have -6. So -6 will be 246.1. So it's right about here. So 246.1. It was 1.2, so right about there is an inflection point. Okay, so that's my inflection point. And then similarly, similar calculation. You have symmetry going on because of the 5 and the 3. So you'll be able to factor out a negative, and it just makes it positive. So it's going to be the same value at positive 6.2. So 246, and then a little bit, and then right about there. Just make a big dot, and that's your inflection point. So the graph comes concave down, and then it changes to concave up, and then goes horizontal, and then concave down, and then concave up, and then goes back up at root 5. So it has to do that little squiggly in there like that. So that'll be hard to do. All right, so what I'm going to do instead is show you my graph, because it's going to be tough to do to sketch that. So this isn't actually to scale, but this is what the graph looks like. All right, so this one is not to scale, but we can try to duplicate it. We're going to use a whole other page anyway. So that's basically what's going on. See how that does that little squiggly in there? That's what's going on right there. So let's try to do that. Why not? Okay, so you're down here, it comes up, goes like that, comes down, flattens out right there, goes down, then starts going concave back up, and then goes root 5. So where did root 5 go? What was root 5 again? 2.2. So yeah, so that's got to turn and go really quickly like that. That's kind of what makes it tough to sketch. Does that. It's not too bad. And then concave. Yeah, that's not too bad. That's pretty good. What's going on? And then these are your inflection points. You can label them as inflection points. And that's what I hate when I graph and not know what the graph looks like. It'll get in the way. Okay, then those are inflection points. So you want to go back and relabel, erase, make it look nice. Okay, and then I found we have already found the inflection points x values. So here's the x values of the inflection points. So that's root 3 over 2. So those would be good enough to, state really most of the time. It's a reasonable thing. I'm not going to ask you to state really crazy numbers and stuff, but just if it's reasonable, state the the exact values, not the approximations. Approximations, we need to get kind of figure out what's going on. This one would take a long time to do it with exact values, but that's the whole process. Long stuff. This took 30 minutes almost. Okay, then we'll do a couple more. It should be a little less time though.